The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Thank you for coming out here in the rain and the day before a quiz. But this is stuff we need to know. So I'm going to be talking about a powerful class of models for communication channels. We've already seen the kind of setup that we're talking about. And so what we're looking to do is model the channel between this point xn. I think my pointer's, okay, there we go. Between xn and yn out there. So what we refer to as the baseband channel. So we've got xn coming in, various things being done to it, and then yn coming out. And we refer to this as the baseband channel. So what's happening in here is things like, let's see, D to A conversion, digital to analog. And then there's the modulation. Then there's the physical channel. I may not have left enough space in this box, but here's the demodulation and whatever filtering. Demodulation and filtering that happens in there, right? So there's distortion. Oh, and sorry, I forgot the A to D, didn't I? So let's stick that back in here. We're doing all our demodulation and filtering in discrete time, so we have an A to D converter here, and then demod and filtering. Okay? And there's various places here that you get distortion and noise. So for instance, the physical channel is a source of noise, but the discrete time operations as well, the computational pieces can also introduce noise. You could have numerical noise because you're rounding off numbers and so on. So there are various places that noise can originate, and there are various places that distortion of the signal can originate. So in the filtering process, for instance, or the channel process, you can get phenomena that will take what started out as a straight edge here and cause it to now get a little bit spread out and not so clean at the edge. Okay, so that's what we refer to as a distortion. So there's all sorts of things in here that can account for that. Now, when we say baseband channel, we're actually trying to distinguish it from the channel that you see after the modulation. So once you've modulated, you've typically moved things to some other frequency range. And so the actual transmission across the physical channel happens in some other frequency range. And so the word baseband here is used to distinguish the channel that we're talking about from that channel. Okay? So this is what we're going to be focusing on. And then we'll later come back to talking about the modulation and demodulation pieces. So last time I introduced a way to represent such models just as systems with an input and an output. One thing I made a point of saying was that when we look at a figure like this, here's a system. We've got some input sequence that's actually going in and maps to some output sequence. So I use this notation with a dot there to indicate the entire time function. Okay, so I've got some entire time function here that goes through the system and gets mapped to some entire time function there. And I'm not telling you the details of how that mapping happens yet, but this is my abstract picture. Now, in many places, you'll see people writing, again, I said this last time, but I want to remind you, you'll see them labeling xn going into the system and yn coming out. And when you see that, you've got to think that what you're looking at is just a snapshot at time n. So this picture is what you get in a snapshot at time n, whereas this picture is the picture that refers to actually mapping the input signal, the entire input signal, to the output signal. Okay? So these are two different ways of representing things. I'm not taking, in this system, I'm not taking the value at time n and producing a value at time n. I typically will need to look at lots of values of the input to figure out any particular value of the output. Okay? All right. I did mention briefly the notion of causality, and we'll come back to that later. But the rough notion is that, or a good enough notion is that the system is called causal if the response at any time depends only on present and past inputs and not on future inputs. Okay, that's easy enough. Okay. And then there were, we were going to specialize actually to the case of linear and time invariant systems. And so I wanted to first introduce the notion of time invariance. Time invariance says basically that if you shift the input by a certain amount, then the output gets just shifted by the same amount, but the same input-output pair works as before. Okay, so what you're really trying to get at is a time invariant system is one where the laws by which you compose the values of the input to get the output don't change with time. So let's see. Let me give you an example here. Suppose I had a system whose input and output were related in this fashion. Would that, do you think, be a time invariant system or a time varying system? I seem to have functions of time in here. Does that make it a time varying system, or is it perhaps time invariant? Yeah? Okay, so time invariant because the law by which you're composing things to get the output doesn't depend on time. So the point is that these coefficients are constant. Okay, so because these are constant, what you have is actually a time invariant system. So to get the output at any time, you're taking 1/3 of the output of the previous time plus twice the input at the present time. And that prescription holds along the entire time axis. So the actual value of n doesn't matter. But if I had here some function of n, if instead of 1/3 I had something like 1/3 to the n, now I've got a time varying system, right? Because the law by which I combine things actually depends on my position along the time axis. All right? So this would be time invariant. This would be not. So that's what this is trying to get at. Okay, easy enough. The other notion was that of linearity. By the way, if you read the chapter, you'll see some other examples that'll help you hone your intuition for what's time invariant and what's not. For linearity, the basic idea was that you can superpose inputs and find the corresponding responses by superposition. So if you've got the results of two experiments, the input in one experiment and the output, the input in a second experiment and the output, and then you take a new experiment in which the input is a linear combination of the previous two ones, the response will be the same linear combination of the previous two responses. Okay, so that's the basic idea here. So linearity means that superposition works, and so this is another feature that we'll use. And for this example on top, do you think it's linear or not? So what you're really, the way to think about it is, suppose I had an experiment A in which my output was Y, in which I fed in XA some time signal and I got a response some time signal. So what that means is that this is true. Okay, this is what it means to say that this is an input-output pair in experiment A. And now in experiment B, similarly, I have YB n satisfying this equation. Okay, so the subscript here just means experiment A, experiment B. So this is experiment A and experiment B. Okay, so now the question you want to ask yourself is it true that if I defined a new input, xn, to be, let's say, what notation did I use there? Well, I didn't want an A and a B, did I? Okay, if you ignore the notation on my slides, let's say that this is an alpha xa plus beta xb. Okay, so here's a new experiment in which I'm going to use an input that's a linear combination of the previous two inputs with some arbitrary weights, alpha and beta. And the question then is the corresponding combination of the outputs in the previous experiment, so alpha yan plus beta ybn, does this xn yn pair satisfy the same equation? Okay, so what we want to check now is it true, well, is it true that the xn here, the yn here, will satisfy the equation on top? And you can see very quickly that it will. And the reason is that yn here is expressed as a linear function of the yn minus 1 and xn minus 1. So when you substitute these in, you'll find that xn defined this way and yn defined this way will actually satisfy that equation. Okay? So this is what superposition requires you to test. So if it's true for every possible pair of experiments here and every pair of weights alpha and beta, that the superposition satisfies the equations governing the system, then what you have is a linear system. Okay? What about if I had changed this to 1/3 to the power n? So I had a time-varying expression of this type. So I have a time-varying system. Do you think this system would still be linear? So if you work through it, you'd see for the same reason that superposition still works. So if I had 1/3 to the n there instead of 1/3, I'd get a time-varying system, but I could still superpose solutions. It would be a linear time-varying system. Okay? Now, we don't want to spend too much time teasing all these apart, because what we'll be focused on is linear and time-invariant systems, and you'll actually come quickly to recognize them. Okay, I defined last time also a pair of special signals, which you've seen before. The unit sample signal, which has the value 1 just at one point, and the unit step signal. So let me just sketch them out for you here. So the unit sample, this is a signal delta n, which is an entire signal. It's not just the number 1 at time 0, it's the entire signal. Okay, that's the unit sample function. There's another notation that's also sometimes used, which is delta sub 0 and dot. So this notation is a little bit more evocative of a function, whereas here you are often tempted to think of it as a number. This says what I'm looking at is a function. It's a unit sample function, and the 1 is at the value 0. Okay? So if you had delta of n minus 3, that would be this function shifted from 0 to 1 to 3. So the value 1 would sit at time 3. Another notation for that would have been this. So sometimes that notation is useful also in making sense of expressions that you're looking at. Okay. So this was the unit sample function and then the unit step function. steps up from 0 to 1 at time 0. Okay? That's the unit step function. And we also talked about the response to these two inputs, so you see them up there. And now my question is, if a unit sample signal at the input produces the unit sample response Hn at the output, and Un produces the step response, and if what you have is an LTI system in here, so it's the same LTI system that we're talking about, can you actually relate the two? So the question is, can you relate the unit sample response and the step response? Do I need to give you both if I have an LTI system, or does it suffice to give you one? So here's one way to think of that. This, by the way, is the same LTI system. Maybe I should indicate that more explicitly by, let's say it's specific system, system 0. And with the same system, I'm trying to deduce the results of another experiment. So if we're thinking superposition, can you tell me how to write the unit sample function as a linear combination of unit step functions, maybe delayed unit step functions, scaled unit step functions? Yeah? Okay. Would it be, you said un minus un plus 1? Or is it un minus 1? N minus 1? So what we're saying is, take this unit step and then subtract from it a unit step delayed by 1. Okay, so here is u of n minus 1. If we took the unit step and subtracted from it a delayed unit step, delayed by 1, the result will be just that value 1 at time 0 will survive, everything else will cancel out. Right? Is that what you had in mind? Okay. So if delta of n can be written as that linear combination of unit steps, can you tell me how to write Hn in terms of unit step responses? We're talking about an LTI system. I took that out, but we're still talking about an LTI system here. Somebody who hasn't spoken, maybe? Yeah?
It should just be S of n minus S of n minus 1.
Yeah, okay. So superposition says that if you've got an input that's a linear combination of inputs for which you know the results of the experiment, then the corresponding output is the same linear combination of the outputs for that experiment. So this is going to be Sn minus Sn minus 1. Right? So you can actually deduce the unit sample response given the unit step response for an LTI system. So let's see, we've used linearity. Have we used time invariance? We used linearity because we said here's an experiment in which the input is a linear combination of inputs that we know the responses to. Where have we invoked time invariance? Anyone? The superposition idea was part of the definition of linearity, right? Because the system is linear, if the input is a superposition of two inputs for which you know the response, then the output is the corresponding superposition of the responses. That seems like I've only used superposition there. Have I actually used time invariance as well? Yeah? Sorry? I've used it in concluding that if I put in u of n minus 1, the response is S of n minus 1. Okay, so I've used time invariance as well as linearity here to come up with the statement. Okay, good. So this is what I have on this slide, and you've figured it all out already. We've arrived at this equation. Now, if I want to turn it around and write Sn in terms of the unit sample response, I can do that as well, except this is analogous to integrating a differential equation. What we have is a difference equation here. And when you come to integrate, well, in discrete time, what you do is summation instead of integration. You need to assume an initial condition of some kind. And so it turns out if you assume that way back in the past, the value of the step response was 0, then you can actually go from this description to a description the other way, relating the step response to the unit sample response. Okay, so if I have a causal system, for instance, so the causal system, it's got no response till the input hits it. So when I put a unit step in, I'm not going to get a response till time 0. And so I know at minus infinity, the step response was 0. And I can move forward from there. Okay, so you can actually relate the step response to the unit sample response the other way as well here. Okay, where the summation is from minus infinity to the n that you're interested in. We'll be dealing right through with causal systems. If there are any deviations from that, we'll point them out. But basically, we'll be dealing with causal systems. Okay, so let's, this is an identity we'll be wanting to play with a bit. So let me put it up here. So the step response, let's say for a causal system, is going to be summation from k equals minus infinity to n h of k. So I take all the values of the unit sample response up to the present time and sum them together to get the value of the step response of the present time. Okay, so let's look at an example here. Here's the unit sample response of a particular LTI system. Is this a causal system? So this is the response to a unit sample. So the input was 0 everywhere except for a value of 1 here. And you see that the response actually happens subsequent to that input. So if the response starts at time 0 or later for an input that started at time 0 or later, then what you're looking at is a causal system here. Certainly in the case of a unit sample response. Okay, so what's the step response going to look like then? Anyone want to say in words? Yeah. This. Okay, so the step response, if we're evaluating it at times over here, we're summing all the values of hk from minus infinity up to the present time. So the step response is 0 here, 0 here, 0 here, and then at time 3, the step response jumps to 1. And from then on, stays at 1, right? So the step response is just that delayed step. And it kind of makes sense because the kind of system we're talking about must be a delay by 3 system here. Because we put in a unit sample input, a unit sample function, and what came out, if you look at it, was actually delta of n minus 3. It was a unit sample function delayed by 3 steps. The height is unchanged, right? The height is still 1. So this must be a delay by 3 system we're looking at. And sure, if we put in a unit step, we're getting, if we put in the unit step, we're going to get a response that's just the step delayed by 3. Okay? I'm going to, sorry, yeah?
Yeah, maybe I'm still confused here, but why is it from negative infinity and to n and not like from n to positive infinity?
This is because of my assumption, assuming s of minus infinity was 0. So I need to have a boundary condition from which I start inverting. So just to go back, let me just go back a second here. Where am I going? Okay, so we derived this first expression if we want to turn it around, well, Sn is Hn plus Sn minus 1. And then I can solve for Sn minus 1. I can keep stepping backwards. But at some point, I need an actual value so that I can close off that expression. And if you're talking about a causal system, then what you're guaranteed is that the step response, if you're talking about a causal linear system, because the all zeros input produces the all zero output, and it's causal, you can actually deduce that the step response at time minus infinity must be 0. The input hasn't yet arrived, therefore the output must be 0. H of 5 is just a number. It's not a function, right? If I write something like H of 5, it's just a number. So it means the value of the unit sample response at time 5. Okay, this takes a little getting used to, but let's do another example here. So here's another unit sample response. This is more complicated now. I put in a unit sample, and what comes out is a response that, well, it still starts at time 0, so I'm talking about a causal system. Everything to the left is 0. And this takes the value 0.2 for some number of steps, and then settles to 0. Okay, so the question then is, what is the step response? And so if you imagine that what you're doing to find the step response at any time is summing this from minus infinity up to that time, you will see that the step response is a linear rise like that, and then it settles out. Okay, so you can get one or the other. And there are other examples on the slides. I won't go through all of them. I'm going a little slow here because we miss a recitation tomorrow. Recitations tomorrow are office hours, so I wanted to actually give you a few examples. Here's a case where the unit sample response increases linearly and then stops. And so the unit step response actually starts to accelerate quadratically and then stops. Okay, this is the discrete time version of integration that we're looking at. Yeah? Oh, sorry, this thing? Yeah. Okay. Ignore that notation. First of all, it's bad notation, but these are figures I got from somewhere. If I was doing it from scratch, I wouldn't have put it in. But I'll explain it. Okay? That's the notation for convolution. I don't actually like that notation, but okay. Examples of this type. Now, here's one important thing for you to get a feel for. Notice in all these examples, the unit sample response settles down to 0 after some time. Okay, so you hit the system with a unit sample function at the input. So you hit it with the value 1 at time 0 and nothing else. And it responds. And it responds for a while and settles. Now, it's not true for all systems that they settle in finite time. Okay, a typical system might ring indefinitely, might respond indefinitely to a kick. All these examples are ones where the system has a transient and then settles down. And so what you expect to see in the step response is there is a transient and then it settles down. The difference is in the step response, it settles to another value. It doesn't come back down to 0. So when this comes back down to 0, what this is settled up to is sort of the integral of this. It's the area under this. But we're talking about discrete time functions, not continuous time functions, right? So the value that it's settled to here is the area under this. So the duration of a unit sample response gives you some feel for how long a transient lasts. So if you've got a channel and you hit it with an input, you know that the transient will last about as long as the unit sample response lasts. So the transient in the step response shows that clearly. You can get more elaborate sorts of unit sample responses. Here's one that changes sign. And correspondingly, what you find with the step response is that it's not a monotonic increase to the final steady state. There's actually some oscillation before it settles down. Okay, but it's the same idea. You're computing the area under this, if you like, but the area goes positive and then slightly negative and so on. Well, positive and then less positive. And so that's what you're seeing up there. Now, why do we talk about step responses so much? Well, it turns out that for a lot of what we do with signaling on communication channels, we're signaling with signals of this type, on-off type signals or plus-minus signals, the sort of square wave type signals or rectangular wave signals. And these can be thought of as combinations of unit step functions. You may have seen this in recitation last time as well. So you can take an input of this type and write it as a linear combination of unit step functions. A unit step function that has its step at 0, minus one that has its step at 4, plus one that has its step at 12, minus one that has its step at 24. Okay, so if you combine those, if you add up all of these, you're going to get that input. So then it's back to this game again, right? If the input is a linear combination of unit steps, scaled and delayed, then the response is going to be the same combination of unit steps. So that's what the response will look like. So here's the unit step un gives rise to Sn. Therefore, minus un minus 4 will give rise to minus S of n minus 4, and so on. So knowing the step response, you can actually say what the response of the channel is going to be. All right, we've seen this visually too. I did an example last time where what went in was that square wave, and what came out after we'd done the demodulation and the filtering was a response that sort of had the features of what went in, but it was a little distorted. So you can see that what we're looking at here, for instance, is the character of the step response, because what went in at this point, right now the input and the output are at rest. Okay, you've forgotten about what happened before, and now the input jumps up. Well, the output doesn't jump up all the way immediately. It's got a little transient before it settles. So what you're looking at is really the step response of the channel, where the channel includes all these pieces. It's the everything including the filtering. In this particular example that I did, if you go back and look at those slides, this was all entirely due to the local averaging that we were doing in the filtering here. But it does give you some kind of a distortion. Okay, so the step response is important to figuring out the shape of the output of a channel. Here's another example that has a more rounded kind of step response, but it's still the step response we're looking at. So here's the input step, and here is the response to the step. Again, there's this notation, and I've said ignore this for now. We'll explain it shortly. Okay, and once you've got the step response of the output, you're ready to start thinking about how you'll detect whether it was a 0 or a 1 that went in. So you might set a threshold, pick times at which you're going to sample, and then you come up with the with your call of what the input is. So 1, 0, 0, and so on. All right? So this seems all benign enough. But now what if you decide you want to get that information across the channel faster? So you want to signal faster. So what you're going to want to do is put that same information, the transition from 1 to 0 to 1, 1, 1, 0, 1, and so on. You want to squeeze that into a shorter length of time. Okay, so suppose this is what you send over that same channel. Well, now you again are going to superpose the step responses. But what's happening now is you've gotten so ambitious with how fast you want to get the bits across that you're not giving the step response time to settle. So over here, yes, there's time. The step response went up and settled because you had 3 1s in a row over there. But now you're going down to 0 for one time instant, and then jumping right back again. Well, here's the flipped over step response, and it doesn't have time to make it all the way down. It's jumped up again. Okay, so if you get very ambitious with your signaling to try and get more of the bits across, you're going to start seeing the limitations imposed by the channel. The channel can only respond so fast, and you can't drive it faster. Okay? So it's important to have a feel for that as well. So when the channel starts to respond like this, you become much more susceptible to noise. So for instance, if there was a noise spike at this point, you could well end up with a received sample that was above the threshold, and then you'd wrongly decode the 0 as a 1. So taking account of the channel characteristics is important when you're setting a signaling rate. Okay, you might want to get information across quickly, but you have to take account of the fact that the channel needs some time. Okay, so much for steps. We'll come back to that later. We can do the same kind of thing with unit samples. So here's And in fact, the rest of the lecture, we're going to be talking about making up a signal as a weighted combination of unit sample functions. So take an arbitrary signal like this. Think of it as, let's see, this starts with a value of something 0.75, I guess, at time -2, and then a value of -0.5 at -1, and so on. So here's your input signal xn. And I want to think of it as made up of a bunch of unit sample functions. So what are the unit sample functions? Well, here's one that's centered at -2, but scaled by the value that the input signal has at time -2. Here's another one centered at -1, but scaled by the value that the input signal has at time -1, and so on. So what I'm basically doing is decomposing the input into a weighted combination of unit samples, right? And you can always do that. And it looks a little magical when you put it into notation like this, but that's basically all that it's saying. So to make sense of this, think, for instance, of putting in an actual number here. So if I wanted x at time 3, well, I'm going to set n equals 3 on the right-hand side and evaluate the sum. Well, the only value that survives is the value for which k equals 3, so I'll pull out x3. Okay, so it's kind of seems tautologous, but it's a way to represent a general input as a weighted combination of delayed unit samples. Okay, so if that was what went in, you're in a position now to tell me what comes out. So I'm talking about an LTI system. I'm talking about an LTI system, and the input xn is a weighted combination with these weights of a bunch of unit sample functions. Okay. Maybe another way that, well, let me actually write this the other way as well. Another way to say this is, here's a time function going in. It's a weighted combination over all possible values of k, of xk times, and this is my other notation, remember, for unit sample functions. So I'm saying this is a unit, sorry, this should be delta sub n. What should it be? Yeah, okay. So this is another way to write the same thing. We've chosen to write it this way, and actually I find that simpler, but if you want to be reminded that what we're talking about here is an entire time function, then this is notation that you might go to. Yeah?
Why the first sum does the upper bound go to infinity instead of n?
Because, okay, good question. Because I'm right now allowing my input to have values that extend from -infinity to +infinity. So I'm taking an arbitrary function. Okay, if we're talking about an experiment in which the input starts at time 0, then we can actually simplify these. I'll show you that. Okay, let me actually erase this because I don't want to confuse you with that. Okay, so if this is what goes in, it's a weighted combination of unit sample functions delayed. What is it that must come out? Okay, so what are we working with? We're working with the fact that if delta of n goes into our system, what comes out is hn. So if it's a weighted combination of deltas that goes in, what's the response, given that this is an LTI system? Someone who hasn't spoken today, maybe? Want to try? Yeah? The same weighted combination of those responses. So it's going to be summation over all k. The same weight, so it's going to be the xk's. But now here's the responses. Okay? So what have we been able to do? We've been able to write down what the output looks like for an arbitrary input in terms of the unit sample response. If you give me the unit sample response for an LTI system, I can write down the general response, the response to a general input. And this is what we refer to as a convolution, or a convolution sum. Okay? That's a convolution. It may look mysterious, so let's actually do it. Let's do it step by step again. Here's our LTI system. If I put in a unit sample function, okay, so this is the unit sample function going in, I get some response. And let's say this is 0, this is 1, 2, and so on. The response we refer to as the unit sample response Hn. So what is this value? This is the value H0. This is the value H1. This is the value H2, and so on, right? Okay. What if what goes in is actually the value X0 at this time and 0 everywhere else? What's the response in that case? So this is just a scaled version of the unit sample function. Instead of 1 going in, I'm having X0 go in. So the response is going to be, what do we have? Same response? Twice the response? What comes out? I didn't hear. Where did that come from? Yeah? X0 times that. Okay, so what we'll get is X0 times H0 coming out at the first time, and then X0 times H1 coming out at the second time, and then X0 H2 at the next time. And if I keep going, I get X0, let's say, Hn at this time, and so on, right? What happens if now it's not that, but it's some value X1 going in at time 1 and 0 everywhere else? So this is centered at time 1, not at time 0, and it's scaled by X1. So what is it I'm going to see at the output? There was a hand somewhere there previously. Maybe you can answer now. Yeah?
The same graph translated 1 over and scaled by X1.
Right, exactly. So what's going to happen is nothing will happen here. I'll get X1, H0, X1, H1, and so on, X1, H of n minus 1. And it keeps going, right? And you keep going here as well. Okay, you keep stringing in these. Each one of these will fire off a scaled unit sample response, but delayed appropriately. And so at the next time, what you're going to get here is X2, H of n minus 2, and it keeps going. And what if you're interested in the value at time n? Okay, so you look along here, and you've come to the value time n. So it's going to be the sum of all of these if your input is the sum of all of these, right? If your input is the sum of all of these x's, your response is going to be the sum of all of these. So what's the sum of all of these? Well, xk h of n minus k. That's all there is. There's no magic to this. It's just invoking linearity. That's the scaling part of it. and time invariance, which is the delaying part of it. Okay? It's as simple as that. All right, so we'll be seeing this notation a lot. You probably recognize this kind of notation from the convolutional coder as well. And we don't want to keep writing these sums. So here's the notation that we use. We say that x is convolved with h, and we are interested in the value at time n. So this operation of this summation here is referred to as a convolution, as I said. I'm telling you what value of time I'm interested in the response at. That's the n. So that's what this notation is. The k here is just a dummy index, right? We're summing over the k. It doesn't matter what I called it. I can call it j, I can call it l. It doesn't matter. The important thing is this n here tells me at what time I'm looking for the response. And that's why that's the argument that I stick in here. Okay? All right. So all that's on the slides, but we've actually derived it ourselves here. Now, again, some gripes about notation. You'll find if you look in most engineering textbooks that this would be written xn star hn. And I can't tell you how much I detest that notation. You'll never find it in a math book. The problem here is that this n is being asked to do too many things. The n is supposed to suggest, the xn here is supposed to suggest we're interested in a whole time function. You would have been better off calling it x dot, but okay, we're used to thinking of xn as also denoting an entire time function. This h is supposed, the h of n is supposed to denote an entire time function, but the n is also supposed to tell you at what time you're interested in the response. So that index is just doing too much work, and it ends up being confused and confusing notation. So, you know, when you're on your downstream classes from here, if you find an instructor using that, make sure that you give him or her grief and say you really can't make sense of that, because this is much cleaner notation. This is what conveys what's actually going on. All right. I'm going to skip over a few things. I just want to suggest some properties here, and then we'll come back to more of this next time. Okay, so it turns out that convolution has nice properties. For instance, the order doesn't matter. You can write x star h here, but it's the same as h star x. And that just comes from making a change of variables in here. Like if I call this m, then k is equal to n minus m, and I get something that looks different, but it's really the same thing. So this is the same as h star x. Okay, so convolution, you can interchange orders. There's some conditions on this, but we can talk about them later. You can associate them, you can group them arbitrarily, and you can distribute convolution over addition of functions. So all of this actually makes it, this is very powerful because it allows you to deal with combinations of systems. And I'll just give you one example and then we'll quit. So here's an example of the kind of thing you can do. Suppose you had an input going into one system, LTI, with unit sample response H1, and then the output of that going into a second system, LTI with unit sample response H2, and then producing an overall output Yn. Well, so how do you get Y? It's H2 convolved with W. I've dropped the argument N because I want to do this just for general values. But W itself is H1 convolved with X. Now, I can group these any way I want. So I can, because convolution is associative, I can put those parentheses where I want. So this is equal to the expression at the end. But that's the same result I'd get by putting this input into a single LTI system whose unit sample response was the convolution of the two individual ones. So I can start to collapse two systems into one equivalent LTI system, and that kind of thing ends up being powerful. But I can also interchange orders. So from here, you can go to this, which then tells you that for an LTI system, if you've got systems in cascade, If you've got two LTI systems in cascade, actually the effect on the output is the same, whatever order the input, the systems are connected in. You might ask yourself whether the same is true if this was linear but time varying. And you should hopefully find out that in general, for linear but time varying systems, you can't do this. So really, linearity and time invariance is what it takes to be able to attain this. Okay, let's leave it at this for now, and we'll pick up again. Well, you pick up some in problem set 4 and also next week.